Hello everyone, this is a video about propagating uncertainties. So I'm going to look at the enthalpy of combustion of ethanol, which you might be doing as part of an energetics lab. So on the right hand side, I've got a load of measurements that have been collected from the experiment. So I've got the mass of the water, which is 100 grams. It was actually 100 cm cubed of volume of water that was collected, but you can convert that to 100 grams of water using the density of water. The specific heat capacity is 4.18 grams, and that's for water. The initial temperature of the water is 23.0 degrees Celsius. The final temperature is 33.0 degrees Celsius. And the delta T, or the change in temperature, ends up being 20.0 degrees Celsius, which can be converted into 20.0 Kelvin, since it's a difference in temperature, so there's no conversion necessary. Then we also need the initial mass of the ethanol, which is 250.94 grams. The final mass of the ethanol once it's been burned to raise that temperature of 20 degrees Celsius. So that final mass is 249.88 grams. And then the difference between those two masses, I've called delta M, which is the difference in mass or the change in mass, and that's at 1.06 grams. Now notice that I have put the absolute uncertainties for each measurement in red, okay? So an absolute uncertainty, I'm going to write that up here, okay, is the uncertainty that's attached to the apparatus or the measurement, right? So, so I've written those in, and you can see that they're dependent on the apparatus that you're using, the kind of how fine the tool is at measuring. So what I'm going to do is I'm going to use this space on the left to do my calculations. So I'm going to start by writing Q equals mc delta T to calculate the value of Q. Now let's slot those values in. So we've got 100 times 4.18 times 20. So 100 grams of water times the specific heat capacity times 20 Kelvin. Temperature difference, okay? And what you're going to do first is you're going to write the absolute uncertainties underneath each of these things. So plus or minus 0.5 cm3. The specific heat capacity has no uncertainty. The 20 degrees Celsius or 20 Kelvin has an uncertainty of plus or minus 1 Kelvin, okay? Now the reason for that is one measurement, so I'm going to go back down to this right hand side, one of those temperature measurements is 0.5, and because we use two of them, we then add those two uncertainties together to get 1.0 Kelvin. So let's maintain accuracy by keeping it to one decimal place. So I'll actually put 1.0 Kelvin here, okay, to make sure that we are not losing accuracy. Okay, so once we calculate that through, what do we get? Let's have a look. So we multiply those together, we end up with let's have a look, 8360 joules, okay, which if we divide by 1,000 to turn it into kilojoules becomes 8.360 kilojoules per mole. Sorry, kilojoules. Let me write that in. Okay, now then, you have to propagate uncertainties, and what that means is you're going to have to turn your absolute uncertainties into percentage uncertainties. So how do we go about doing that? Well, we use this formula over here where we do the absolute uncertainty divided by the measurement that you made, and then you multiply that by 100. So let's just use this space on the left to work out the percentage uncertainties. So let's do it for the 100 grams of water. So if we do it for the water, so this is the percentage uncertainty and this is for the water, okay, mass. So what we'll do is we'll do 0.5 and we'll divide that by 100. So yeah, because that's 100 grams of water, and then we multiply that by 100 to make it a percent. Obviously these cancel out, so the percentage uncertainty for that water is actually 0.5%. Okay, now for the percentage uncertainty for the temperature, what is it? It's going to be, so let's do this down here, percentage uncertainty for the temperature. So that's going to be 1 divided by 20 multiplied by 100%. Okay, so those cancel out. So I've got 1 times 10, which is 10. So 10 divided by 20. Divided by 2. Get my maths right. So 10 divided by 2, which means we end up with 5% as our uncertainty for temperature. Now that we've worked out the percentage uncertainties, we're now going to try and propagate those next to each of the values in the calculation from the values that we measured in the experiment. So let's go over to the calculation. I've already written it out over here. Okay, so what we're going to do now is we're going to add the absolute uncertainties, and I'm going to draw those in red so that you can see them clearly. So we write a plus or minus 0.5 grams next to that 100, and we write plus or minus 1.0 Kelvin next to that 20. Okay, so those are the absolute uncertainties. Then we've got to write the equation again underneath. And this time we add the percentage uncertainties underneath. So this ends up being 0.5% as the percentage uncertainty that we worked out. And the 20 has a plus or minus 5% uncertainty. Then we've got our answers. Okay, so what we do at this point is we add our percentage uncertainties together. So when we add our percentage uncertainties together, we end up with 5.5% as our total percentage uncertainty for this value that we calculated. And then what we do is, if we're obviously going from the first value to the last value here, we've divided by 1,000. Okay, so it's still plus or minus 5.5% for the percentage uncertainty. But then what we're going to do is we're going to turn that back into an absolute value. How do we do that? Well, what we're going to do is we are going to work out what 5.5% of 8.360 is. Okay, remember this is in kilojoules. So what's 5.5% of that? So what we can do is we say mathematically we put 5.5 divided by 100 and we multiply that by 8.360. And when we calculate that through, we end up with 0.4598. And because we're working out a proportion of that 8.360, then the answer that we get is in kilojoules. So we're working out an absolute uncertainty of that final answer. Okay, so if we go back up here, we can then add the absolute uncertainty back to this number. So we'll do plus or minus, in fact I'll write it underneath. Let's do it here. So plus or minus 0.4598, and that's in kilojoules. Now, if this value that we calculated is the final value for your answer, we have to be careful about significant figures. So we will make the final percentage uncertainty to 1 sig fig, so that's 6%, from 5.5% to 6%, and that's 1 significant figure, or 1 SF. And that our final absolute uncertainty would also be 1 significant figure, which would be 0.5 kilojoules. Okay, now that's if it was the final answer. In this case it isn't, because we'd have to turn that Q value into delta H. So if this was the final answer, what would we do in terms of working out the final significant figures? So if we look at the final percentage uncertainty, that is usually rounded to 1 significant figure if it is above 2%. Okay, so if the final percentage uncertainty is above 2%, then we round it to 1 significant figure. If the percentage uncertainty, so the final percentage uncertainty, if it's less than 2%, so it's like 1.5 or 0.05 or something percent, then we round that to 2 significant figures. Okay, Now then, the final absolute uncertainty, remember these are what we have next to our final answers, okay? Our final answer. So it might be the enthalpy of combustion of that alcohol. So the final absolute uncertainty is usually rounded to one significant figure. Okay, now these rules are not set in stone, but they're like guidance on how to make your answers look a little bit tidier, and with, you know, and also at the same time respecting the accuracy of your measurements. Now, if we go back to the final answer, okay, remember that we need to put a plus or minus next to our percentage uncertainties. Okay, so if I round it to one significant figure here, it's going to be plus or minus 6%. And if I've rounded it to an absolute uncertainty of 0.5, then that's also a plus or minus figure. So I'm just going to move these across to make them look a little bit neater. But that's what the answer should look like when we finish. Okay, so your answer is that 8.360, and it's plus or minus 6% or plus or minus 0.5 kilojoules.